system of equations, solutions for linear system of equations, where we are solving AX equals B. A is basically known matrix, known coefficients matrix. X is your variable unknown, and B is again your known output vector. Okay, X is basically also, you can call it as an inputs, and B is basically an output. And so far we basically saw that if we have a square system, basically for an n by n system, we use Gaussian elimination, LU decomposition, then we did Cholesky factorization, and then we switched our conversation or discussion for system of equations when the system is no longer square. That means the size of A is no longer n by n, but is m by n, where m can be greater than n or m is less than n. When m is greater than n, then we basically call this system as skinny matrix, skinny A matrix. And it is also called as overdetermined systems. Overdetermined systems. When m is less than n, we call as fat A matrix. And it's also called as underdetermined systems. Okay, so why it's called skinny? Because if you look at the overdetermined system, that's what we basically learned, or we were basically covering or discussing in the last lecture, when we have large number of equations but less number of unknowns. So overdetermined system is something like you have, I was taking the example of a data point, fitting a straight line through a bunch of data points. So this specific A matrix has got 4 rows, 2 columns. It has got 2 rows, 1 column. This has got 4 rows, 1 column. So the way the matrix multiplies, or matrix multiplication can happen, then the number of columns of the first matrix should be equal to the number of rows in the second matrix. That has to be same. Otherwise, matrix multiplication cannot happen. So you have to always remember. And the output of this matrix multiplication would be a vector which has got this entry times this entry, which is this 4 cross 1. So while you are doing matrix multiplication, make always sure when you're doing implementing in MATLAB or any code that your number of columns in this matrix must be same as number of rows in this matrix. And the output would be the number of rows times number of columns of that. Is everybody with me so far?
Yeah.
Yeah.
Any questions, guys, so far? So this is called skinny because it has got this in one dimension. It is basically a bit longer than the other dimension. That's why I call it skinny matrix or skinny A matrix. This is again your normal traditional X vector. Let's call it X tilde vector. Basically, it is normal unknown vector. This is your A, and this is your normal Y vector or Y tilde vector. Now, solution for that, as you know, what this problem basically represents is that you have a bunch of data points represented by x1, b1. Just a second. You have x2, b2, x3, b3. This is your x and this is your y, and I'm representing this as points which has got coordinates x4b4. And what this specific formulation is doing, it is trying to fit a straight line through these data points. Now, there are many ways you can fit a straight line. You can fit a straight line like this, or you can fit a straight line like that. It can also go like this. So there can be many possible ways that a straight line can be fitted through this set of data points. Now, what we are interested in is to fit a straight line such that the error from each of these must be as small as possible. For each of the data point, if you see the y value, the actual y value is b1, but from this line, the y value is I'm getting is y1 here. I'm getting y2, I'm getting y3 and y4. So the errors that I'm getting has to be minimized. And what we see in the last lecture, the last part of the discussion, we are saying that we generally call that solution as least square solution. And what the least square solution says that the value of this unknown is given by A transpose A inverse times A transpose times Y tilde matrix, where Y tilde is this, basically this known vector. So if you do this multiplication, and you will basically be able to solve for these unknowns, C and M. The equation of a straight line is represented by y is equals to mx plus c. So this m is unknown, slope is unknown, and your c intercept is unknown. So you are solving for that. If you can solve for this, that means you know the equation of a straight line. You can draw that line if you can find m and c, which is slope and the intercept. And this formulation is actually trying to solve for that in slope and the intercept. And when you solve this, you actually can use this formula. This is a very, very powerful formula used many control applications, or any system of equations where it is an overdetermined system, or you want to fit some polynomial to a data points. Any situation where you have an overdetermined system, you basically go for this least square solution. Least square solution is basically you minimize the error between the function, which is your straight line, and the data points. Is everybody with me so far?
Yeah.
Yes.
For anybody, other students in the class, are you with me?
Yes.
Yes.
Okay,
Professor.
any questions so far? So I uploaded a bit of a piece of code as well in the Beachboard. I hope you get a notification and you can also download it and run it. So I showed it in the last lecture, how basically we can get a straight line by solving this system of equations. Now, this solution is not only constrained to fitting a straight line. For example, now let me take another example. So I will start with this. The same data points, x1, b1, x2, b2, x3, b3, x4, b4. So let's say I want to fit a polynomial curve through this set of points. Okay, so what I would like to do is I want to approximate or fit a polynomial through the set of given data points. Right now I have only 4 data points. So let me actually, okay, let me also write the form of a polynomial is generally given by a0, a1x plus a2x squared, so on, plus anx n minus 1. Actually, anx n, sorry. Okay, so let me actually randomly pick a student from the participants here. So let's say if I ask Vanessa.
Yes, Professor.
So if I have to fit a polynomial, what is the largest degree of polynomial I can fit through these 4 data points?
Let's say 4.
So you mean
Oh,
4-degree polynomial, right?
yes.
So, okay, let's see what a 4th-degree polynomial will look like. It will be a0 plus a1x plus a2x squared plus a3x cubed plus a4x4. How many unknowns we have in this?
1, 2, 4.
How many unknown coefficients we have? Because these are my
Oh, the coefficient's 5.
5. And how many data points I have got?
Oh, okay. So there are only 4.
Yes. So basically you can only fit a number of data points minus 1 always. So if you have given 4 number of data points, it means you can only fit 3-degree polynomial exactly. Does it make sense?
Yes, so it's going to be 3 degree.
Yeah. So since I have unknown coefficients of the maximum degree polynomial that I can fit, that can fit through n given data points is n minus 1. Yeah.
Yes, Professor.
Everybody's getting that? Yeah. Everybody.
Yeah. Yes.
Okay. So let's say if I have to fit a exactly 3rd-degree polynomial, because I have 4 points, I can fit exactly 3rd-degree polynomial, which is cubic polynomial. So what I can write px as that can be fitted is a0 plus a1x plus a2x squared plus a3x cubed. Okay, that is the polynomial you can directly fit. Now what I am given is a table of the values that represents my xi's and y's. So I have x1 b1, x2 b2, x3 b3, and x4 b4. So what I basically can do is I can determine these coefficients a0, a1, a2, and a3. How? So I know that a0 plus a1 x1 plus a2 x2 square plus a3 x3 cube is equals to b1. Yeah. If a polynomial that exactly passes through, let's say the polynomial looks like this. Okay. So the polynomial, this is the polynomial, which is a cubic degree polynomial, which is given by this cubic function. Now these a0, a1, a2, a3 are unknown to us, and we need to determine these coefficients. So how can we determine that? We can use this data point. So we can use a0 plus a1. Instead of x, I plug x1, and I should get b1 because that is what I'm getting. Is everybody with me?
Professor,
Yes.
1 and x1 square and x1 cube or x2 square?
Yeah, you are right. Thank you for correcting. These are x1s. Okay. Similarly, P of x2 would be a0 plus a1 x2 plus a2 x2 square plus a3 x2 cube is equals to b2. Is everybody with me?
Yeah.
Yes.
Yeah. And similarly, you have for p x3 and x4, and you will see it is a0 plus a1 x3 plus a2 x3 cube plus a3, sorry, x3 square plus a3 x3 cube is equals to b3. And similarly for x4, it will be a0 plus a1 x4 plus a2 x4 square plus a3 x4 cube is equals to b4. Yeah. Now, if I have to represent this in a matrix form, what I will do, what I will get in matrix form? What I will get is I can write this system of equations as 1, x1, x1 square, x1 cube, 1, x2, x2 square, x2 cube, 1, x3, x3 square, x3 cube, 1, x4, x4 square, x4 cube, multiplied by a naught, a1, a2, a3 is equals to b1, b2, b3, b4. Let me know if everybody follows that.
Yeah, that makes sense. I was having trouble seeing um, where the A1s, but yeah, it's the other 4x1 matrix being multiplied to it.
Mhm. So is everybody following that so far with me so far?
Yes. Yeah.
Any questions from anyone? Or if you are not following it, please let me know. I will try to explain again. Okay, so it seems everybody is following it. So now you see this is a 4x4 system. I mean, it is a square system. It has got square, I mean, 4 unknowns. I have got 4 equations. Now, if I need to, these are already given to you. You know what your x1s are, your b1s are, because this table is already given to you. Data points are given to you. So you can solve for this using Gaussian elimination. You can use it using LU decomposition. You can solve it using Cholesky factorization or any other method. So you can solve it and you can find A0, A1, A2, and A3, and you will see that you will find the polynomial actually fitting all through these data points exactly. Is everybody with me so far?
Yes.
Yeah. Now I change the problem and I say that, okay, instead of cubic, fit a second degree polynomial through these data points. Then what you basically do, you basically then see that now you are not having this term when you are basically trying to fit a second degree polynomial, isn't it? This term will go away, right? So
Yeah.
you will basically have px is a0 plus a1x plus a2x squared. That's it, because there is no third degree polynomial, because I want only a fit. That is a given condition. You do not want to go for cube third degree. You want to go to second degree polynomial. Yeah. And then what we actually have, we still have 4 equations, but we were not going to get a polynomial that will pass through all these points equally. So you probably will get a quadratic polynomial which goes like this. It will not pass through these points. What it will do, it will actually go like this, depending on what your coefficients are. So if this is your second degree polynomial given by a0 plus a1x plus a2x squared, because a second degree polynomial cannot pass through arbitrary 4 data points equally. So what we actually do, you then use the least square solution, where you see that the polynomial must have the errors between the data points as small as possible. So these errors should be as small as possible. So then if you use this specific polynomial, the matrix form, let me ask somebody from the class, what is the matrix formulation you will get? So I will get the same. So this is for second degree polynomial. I still have 4 equations because I have got 4 data points. So I will got 1 x1, x1 square. I will not have an x cube term now. 1 x2, x2 square, 1 x3, x3 square, 1 x4, x4 square. So somebody I will ask randomly from the class has to help me with what these coefficients will be. So B1, B2, B3, B4. So let me now randomly pick a student from the class. How about Victor Lopez?
Yeah, it would be A0, A1, and A2.
Perfect. So A0, A1, and A2. And this will be your unknown X. This is your known A, and this is your known B. In this situation, you are going to use that square solution where it will be A transpose A inverse times A transpose times B. Okay, and this solution will give you the best polynomial, best second degree polynomial that has the minimum error from all the data points. That's the best fitted second degree polynomial. Make sense?
Yeah, Professor, one question.
Yep.
The least squares solution, will that output just your slope and your intercepts for the function, or rather just your A constants?
It will solve for these unknown coefficients. So instead of for second degree polynomial, let's say I want to fit a straight line for a first degree polynomial, which is a straight line. Now, instead of saying that I want to fit a polynomial, I want to fit a straight line. Okay, so straight line is, just give me a second. Okay, so instead of cubic polynomial and square polynomial, I want to fit a straight line through these data points, if that is the given task. So for given task, then the equation of that straight line would be P of X would be A0 plus A1X, right?
Yeah.
Yeah, this will be your slope and this will be your intercept. So in this matrix form, the A's and B's will remain same, except now you will have, sorry, A will change as well because now you have only linear terms. And you have here A0 and A1, these are the two unknowns. And you have the same B1, B2, B3, B4.
So the output of the least squares solution applied to the second degree polynomial will just be a 3x1 vector?
Yes, it will be this unknown, 3 by 1.
I see.
4 by 3, 4 by 1. So here it is 4 by 2, 2 by 1, 4 by 1. So the output of this, you can verify that itself. I will basically say, ask everyone in the class to see what is the order or what is the dimension of this specific matrix would be. If A is given as 4 by 3 and B is 4 by 1, what will be the output of X? What is the dimension of X? Can you quickly find it out?
Repeat the question, Professor.
My question is that if you know the dimension of A matrix is 4 by 3, 4 cross 3, 4 rows, 3 columns, and you know dimension of B vector is 4 cross 1, 4 rows, 1 column. What is the dimension of this X vector would be? X least square solution.
3 by 1.
How much?
3 by 1.
And how do you get that?
Just it matches A.
No, I don't want you to look at this and say, okay, it matches. I want to actually use this expression and find it out. What would be the dimension of this matrix? This is a matrix multiplication. You agree?
Yes.
Yes.
So can you do that dimensions and check what will be the dimension from this matrix multiplications?
It would be 4 by 1.
4 by 4.
Do it, please. I mean, take 1 minute. I'm giving you a minute. It's 6:03. I'll go for 6:04 and I will ask. Eventually, you should get 3 cross 1, but I want you to experience it yourself that you are indeed going to get 3 cross 1.
I got 3.1. 3 times 1.
Yeah, I want every one of you to actually do that and see it yourself. And if you're not, then I will help you to do that. Is everybody getting it?
Yeah, I have 3 by 1.
Yes, Professor.
Or I will randomly pick somebody and ask. Let's say I have here Kyle. Kyle. Okay, we don't have him, I believe, here. Then Denzel.
Yes.
Yeah, so can you help to find out what the dimension of this? So what will be dimension of A transpose A?
It should still be 4 by 3, right?
No, it will not be. A transpose. What is the dimension of A transpose?
Oh, it should be a 3 by 4.
Right, so 3 cross 4. Dimension of A.
4 by 3.
So what is the dimension of these two matrix multiplication going to be?
Um, uh, 3 by 4.
So I said that this has to be same and the output will be the first row and second column. Okay. So it will be
Got
3
it.
cross 3. So that the output of A transpose A will be 3 cross 3 and inverse of that will be again 3 cross 3. So 3 cross 3 multiplied with 3 cross 4. What will be the output, Denzel? So this is 3 cross 3 multiplied with A transpose, which is 3 cross 4. What will be the output? What will be of that matrix?
3 cross 4.
3 cross 4, perfect. And this multiplies with B vector, which is 4 cross 1. So 3 cross 4 multiplied with 4 cross 1. What will be the dimension?
3 cross 1.
And that's what it is, right?
Yeah,
Got it?
got it.
So is everybody with me following it so far?
Yes, Professor.
Great. So that's basically, you can see that when you're trying, and these are the steps which you have to do it yourself to see whether the solution that you are getting makes sense. Because as I said, if I'm not giving you the solution, how will you make sure that the solution you are getting is correct? So at least the first step is the dimensions of the unknown vectors are getting correct. So that's important. Second thing is the solution makes sense, whether it is basically passing through, it seems to be passing the data points, whether the error seems to be minimum. So those are basically some qualitative checks you can do it yourself. Anyways, coming back to the topic where we are talking about the least square solution. So I have got 4 data points. If I have to fit a polynomial, I can exactly fit third degree polynomial, which is a cubic polynomial, because maximum degree of polynomial that can be fitted through n given points. Here we have 4 points is n minus 1, which is 3. So we can fit 3 data points exactly. And when we write these equations in a matrix form, we can solve for this uniquely. So unique solution we can get. But if now the problem changes, if somebody says, no, I don't want a cubic polynomial, I want a straight line to be fitted. Now, if you want a straight line, it has got only 2 unknowns, A0 and A1, but I have got 4 data points to take care of. So what we will do, basically, then we will go for this least square solution. Least square solution is a solution that gives you minimum error between the assumed polynomial and the number of data points. So it is the solution that gives minimum error between the given data points and assumed polynomial function, where assumed polynomial can be a linear, can be square, anything which is less than 3 for this given set of data points. Make sense?
Yes, Professor.
Yeah. Is everybody with me and you are basically understanding what we are discussing here?
Yeah.
Yeah. Any questions, guys?
I didn't get to see what was at the bottom really quick that you wrote. There we go. Thank you.
Okay, so the next step is, now we have seen the least square solution, which is for overdetermined system. Overdetermined system basically means your M is greater than n. Now, second part is when m is less than n, what will happen then? So I'll just take a small, simple example here. So far, everybody is with me? I mean, is everybody following it so far, what we are discussing?
Yeah.
Yes.
Yes, Professor.
Yes. Okay, so the next step is underdetermined system or fat matrix. Underdetermined system or fat A matrix. So we are still solving AX equals B. Now instead M cross N, we have M less than N. That means my A matrix will look like this. I have more number of unknowns and less equations. So for example, let me say this, A0, A1, C, M, B1. So basically you have here 1 cross 2 times 2 cross 1 is equals to 1 cross 1. It's basically dimensions are matching what we need to match, because here you have rows and columns and rows matching, and the output would be 1 cross 1, which is here. Now, what this system is representing? It is representing a fact. First of all, it is, you have got how many unknowns here?
2.
2. And how many equations you get?
1.
1. So basically it is an undetermined system, unknowns, and only one equation. So there is again no solution, no unique solution, but you can still for the system of equations in some sense. When we say, when you solve a system of equations, we are not solving unique solution for C and M. C and M basically, again, I'm using these variables. It will be clear in a second. So here I have only, let's say, one data point, X1, B1. And I ask you guys to find a equation of a straight line that passes through that point, that passes through this point. So find an equation of a straight line y equals mx plus c that passes through the given point, given data point. Okay, so let me randomly again pick a student. So can we have Phi Gwen?
Yes, I'm here.
Okay, so can you tell me what will be A0 and A1 if this is the equation you want to fit?
It could be y1. No, wait, hold on.
So C and M are unknown, which are here.
Yes.
And what will be this, and what will be A0 and A1? If you have to, you write this equation in a matrix form, how will you write it?
It could be x.
Yeah, so basically you will get the same thing as we did.
One x1, y1, b1. Yeah.
Yeah, exactly. Thank you. So that is exactly what we were solving it. But now instead of having 3 equations, I mean 3 data points, I have only 1 data point, and I only have 1 equation to solve for these 2 intercepts. So let me pick another student from the list of students here. How about Karthik? Karthik? Okay, if not, Mohammad Qasim?
Yes, Professor.
Okay, so if you have to intuitively tell me how, or you intuitively tell us that how many straight lines you can pass through this.
And infinity.
Infinite. So, and that is what you will get. This system of equations will have infinite solution. Infinite solution. And the reason it can have infinite solution, because I can pass a straight line like this. I can pass a straight line like this. I can pass it like this, or any other way. Is everybody with me following it?
Yes.
And every straight line has got a specific slope and intercept, specific m value and c value, every straight line. And there are different infinite possible ways. Now, when we would like to solve this type of undetermined system, the generic or the general requirement is that the norm of the solution vector has to be minimum. One particular solution of interest, which is always the case out of infinite possibilities. Norm of a solution has to be. Now, what is a norm basically? The norm is that, let's define what is a norm of a vector. So norm of a vector measures the length in a specific reference system. So for example, if I have a x and y coordinate system and I have a vector which is given by x1, b1. So can somebody tell me what is the length of this vector would be?
Is it the square root of x1 squared plus b1 squared?
Yes. Perfect. Now, if I have in 3 dimensions, what will be the what will be the norm? It will be x1 squared plus b1 squared, y squared plus z1 squared, isn't it? Yeah. So norm of a vector, specifically L2 norm, we call this as L2 norm or Euclidean norm, is given by of a vector. Vector is represented by x, and the norm is given by 2 double lines on the start and the beginning, is given by the square root of the sum of the square of the elements of the vector, and so on. If the vector is of n cross 1 length, it has got n elements, and that is the L2 norm of a vector, of a n dimensional vector. Does it make sense, everybody? It's a formula, and basically this formula, the physical interpretation of this formula is that this specific formula represents the length of this vector. So if it has got 2 dimensions, it has got 1 dimension. I mean, if your x vector has got x1 and y1, and the length of this will be x1 square plus y1 square square root. If your x vector has got 3 dimensions, x1, y1, and z1, then the length of that vector will be square root of x1 square plus y1 square plus z1 square. That is the L2 norm. Yeah?
What's that symbol they used before A? Yeah.
Here?
Yeah. What is that symbol?
This is for vector, denoting that it has got a bar on top of it. It is a vector magnitude. OA is a vector.
Oh, OA. Oh, thank you.
Yeah. Is everybody following it so far?
Yeah.
So norm or vector norm is basically measures the length in a specific reference system. Now there are different types of norms as well, infinity norm, L1 norm. We will come to that later on. But at this point, let's physically, what does it mean? It means how can you determine the length of this vector? So to determine the length, one of that norm is called as L2 norm, and it is basically the square root of the sum of the square of the elements. If it has got 2 elements, the length is given by square root of x1 square plus y1 square. If it's got 3 elements, it will be the length of that vector would be square root of x1 square plus y1 square plus z1 square. And if it has got 4 dimensions, it will be added up. If it has got n dimensions, it will just keep on adding. And that will be your L2 norm. Now this L2 norm of the vector has to be minimum. That is a specific interest. And for that, the solution is called as least norm solution. And it's the same form, but slightly different. Least norm solution. So instead of the form that we used earlier, A transpose A whole inverse times A transpose, now the form is A transpose will be outside A times A transpose inverse times the Y vector or the B vector, where this is your A matrix, this is your X unknown, and this is your Y known. This is called as least norm solution. And what it says that out of all possible straight lines, you are going to get an equation, or you are going to get a solution that has got the least length or the minimum length of the vector. If you take the square root, if you take the sum of the squares and take the square root of this vector, then it will be minimum using this specific solution. Are you getting it or not? Let me know.
Does that
Hello?
make C equals 0, Professor?
Come again, sorry?
Doesn't it that make C equals 0 in our case?
Which one?
So for the example that you're solving, so that makes C equals 0, right?
No, it will not. Because if, okay, let's take this specific example, and let me say I'm giving you 3 options. So one of the option you just said, setting C equals 0. If you set C equals 0, that means that straight line looks like this. Okay, that is the equation of a straight line that has got some value of m, but the C is 0. C is 0 in this case, yeah?
Yes, Professor.
So that is one possibility. Another possibility is that you actually get a straight line that looks like this. That has got y equals C1x, C is some value, m is 0 in this case. The slope is 0, yeah? This is m0 and this is C0, yeah?
Yes, Professor.
Yeah, so there is another solution which is given by this solution that will be look like this, which still passes through that. This has got y equals m to x plus c2, such that if you take the norm of this vector, norm of the vector means you have now 3 vectors. One vector is c is 0, m1, that is one vector. Another vector is C is non-zero, M is 0, and another vector is the least norm solution, which is given by M2, C2. And if you take the length of these, you will find that this is the solution that has got the least length of all the possibilities. So let me actually ask you guys, somebody from the class, that if you are getting it or not. So let's say if I have Roosevelt.
Yeah, can you actually go over that one more time?
Yeah, let me actually go over that one more time.
Thank you.
Professor, how do you quantify the length? Because to me, it's hard to understand a line of having infinite length being quantifiable. Am I correct?
Infinite length. Okay, so we are not quantifying the length of a line. We are quantifying the length of a vector. And the vector has got elements x1 and y1.
I see. Thank you.
Yeah. Okay, so what I was saying, that if I have to pass a straight line through that, the equation that I have got is this. And as I said, the least norm solution is given by, this is your A matrix, fat matrix, or an undetermined system means you have less equations, more unknowns. This is your x vector and this is your b vector or y vector. So the least norm solution is x least norm is given by A transpose inverse times y. That is your least norm solution. Now this solution will give you a specific value of this unknown vector. So let's say that is C2 and M2. That's what you are getting out of solving that. And okay, so let's actually pick some number here. So x1 is, let's say 2 and y1 is 3. So x1 and b1 are known to me now. And if I have to solve for this least norm solution using this, I'm getting C2 and M2, which you can easily solve. Can somebody solve that for me and let me know what C2 and M2 would be? If you have this, instead of x1, you have 1, 2, C and M, and 3. So A matrix is 1, 2. I mean, it is just a vector, and Y is 3. So if A is 1, 2, then A transpose, let's do it actually here, least now. So A transpose would be 1 and 2 in the column because row will become column. A is 1 and 2. A transpose is 1 and 2 in the column, and you take the inverse of whole of that times y. Y is your 3. So let's do that actually. So if I actually multiply this first, 1 times 1, 2 and 1, 2 here. So what I'm getting here is 1 plus 4, which is 5 inverse. And here I have 1 and 2, and here I have 3. So eventually what I'm getting here is 3 over 5, 1 and 2. That means my C2 and M2 are given by these numbers. So 3 over 5, and this is 6 over 5. So your C2 is 3 over 5, and your M2 is 6 over 5. Is everybody with me?
Yeah.
Yes.
Is everybody from the class with me, or you're not following it? I will try to explain again.
Yeah, I'm following along.
Okay, so now I got this vector. Now what is the L2 norm of this vector would be? If I have to find an L2 norm of this vector, what is the length of this? It will be C2 square plus M2 square square root. So what do I get? Square root of 9 over 25 plus 36 over 25. Can somebody tell me what the number would look like? It is square root of 44 over 20, 45 over 25 actually. So it is 9 over 5. Anybody can tell me what the number would look like?
$1.3416.
1.3416. So that is the length of that, the L2 norm of this vector. L2 norm is length of this vector is 1.3416. So if I have a straight line that has got intercept 0.6 and M2 slope is 1.2. So basically I am having a straight line that passes through this, which has got a equation 6 over 5x plus 3 over 5. So this is the straight line. This is a least norm solution. Least norm solution. What it means that this technique or this specific solution gives me an equation of a line such that the vectors, the unknown elements, has got the least length. It has got the length which we got as 1.3416. Now somebody tells me that, okay, how about if I draw a line like this? So if I draw a line like this, what will be the equation of a line? Let me actually ask somebody from the class. Okay, how about Vincent? can you tell us the equation of y equals 3? Perfect. So y equals 3. So that means what is, okay, so Vincent, can you tell me what is the value of m and what is the value of c in this case? Yeah, m0 and c3. So can you tell me can somebody else tell me what is the length of this vector, or L2 norm of this vector would be?
Three.
It will be 3, right? L2 norm would be 3. L2 norm would be 3. And you will see that this L2 norm is much, much greater than the L2 norm of this. L2 norm of this is how much? 1.3416. That's what you actually figure it out. So L2 norm of, here you have M as 6 over 5, C as 3 over 5, and L2 norm is 1.3416. Now somebody tells me, okay, how about if I pass a line through the origin? So if I pass a line through origin, can somebody volunteer and tell me what is the equation of that line would be? Can somebody, any volunteer from the class, tell me what will be the equation of this line passing through this point?
Over 2x.
Sorry?
Y equals 3 over 2x.
Y equals 3 over 2x. So is everybody with me? Everybody is getting that? And if we have this, what is the value of m and what is the c?
M is 3 over 2 and c is 0.
0. And what is the L2 norm of that?
1.5. 3 over
1.5. And what is the one we are getting with our solution? 1.3416, right?
Yes.
So no matter whatever way you actually draw a line, you can basically test it with any condition like you want. You will see that this solution will always and always and always give you unknowns that has got the least L2 norm, least L2 norm. That is what we call as least norm solution. It has got least L2 norm. Does it make sense?
Yes, Professor.
Yes.
So if somebody says, can you solve an undetermined system of equations? So this is an undetermined system of equation. Undetermined means that you have less equations, more unknowns. Undetermined system of equations. Then your answer would be, first, there are infinite possibilities. And out of that infinite possibilities, if you are concerned or if you want a least norm solution, then I can tell you what the least norm solution would be. But if you are not interested in least norm solution, you are interested in infinite possibilities, you can pick any value of c, you can solve for m, or you can pick any arbitrary value of m and you can solve for c. So there are infinite possibilities. But out of those infinite possibilities, if we are concerned about least norm solution, this is the way to find out. Make sense, guys?
Yes, Professor.
Any questions so far?
Not at this time.
Sorry?
Not at this time, Professor.
You're good guys, right? Everybody is following it so far?
Yes.
Yeah. So I can quickly switch to my computer screen. And I believe this code is also I uploaded just a while ago. So this is the least square solution I was basically showing you in the last lecture. I have got more number of data points, but I'm just passing a straight line. So I'm just having my A matrix is just 4 cross 2. I have got only one, two unknowns, but I have got 4 rows here. So when I actually, you can basically run this code and you will see that you can change the data points arbitrarily, and you can see that this is a straight line that will best fit this data points. Now this is, you can change the data points, but when you have to change the data points, you have to change the x coordinate and y coordinate, and you can see how the straight line changes. Now you can change this code to basically fit a second degree polynomial. You can change this code to fit a cubic degree polynomial. That will be a part of your homework exercise that I will be posting later. But this actually gives you least square solution. Least square solution means you're interested. First of all, you are solving the overdetermined system. Overdetermined system means you have more equations, less unknowns. And here the objective is how can we fit a curve such that the error between the data points, the given data points, and the value given by your approximating function or polynomial is minimum. And the other case is undetermined system. Actually, it should be underdetermined. It must be, I have not changed this statement. So please change that when you copy it from the beach board. So underdetermined system means you have less equations, more unknown. So I am just using one fixed coordinate. And when I run this, you see that it passes through straight line, and actually it should be least norm as well. So you get the slope, intercept and the slope, and you see that this is a straight line that passes through the data point, but at the same time it has this length of this vector will be the minimum norm vector. You can pass any straight line, but this specific vector will have the least norm. Least norm means it has got the least minimum distance of that vector, minimum length of this vector, unknown vector. So minimum length means not the length of this line, but length of this specific unknown vector which we are solving for. So if I change these points to, let's say 1, 5, you will see that the line will change, and you have got different values of C and M. And this is the, out of all possible infinite possibilities, this is the one that will give you the least norm solution. Okay. Any questions, guys?
I got one.
So these codes are already there in the beach board. You can basically download and you can basically play with the numbers and values, and there will be some homework exercises based on these codes where we will basically need to solve for some fitting curves or some other objectives. So I will actually post that soon. But any questions so far in understanding the overdetermined system and undetermined system and how to solve for them?
Professor, in the code, where do you specify the polynomial? And
No, I don't specify a polynomial. I specify this A matrix. So instead of saying that I have a straight line, I just specify the size of this polynomial, or basically the matrix.
oh, okay, so we'll have to just add another row if we have a polynomial.
Yes. So in the least square, if I have I have straight line, if I have a polynomial, you have to add another row for second, basically the second coefficient, x square.
Okay, thank you.
I can show you, just I'm showing you here, x squared 1. That will be your second column here. Does it make sense?
Yes, Professor, thank you.
So let me actually go back to the document. So what we were actually discussing is this specific equation matrix. I'm just running out of batteries, so my computer can stop anytime. Just give me a second. Let me plug my charger. So what we were discussing is that so when I was basically trying to fit a straight line, my A matrix was built like this. But if you are going to fit a second degree polynomial, A matrix will look like this. If you are going to meet a third degree polynomial, A matrix will look like this, and B matrix will look like this. Okay.
Got it.
Yeah. Any questions, guys, so far?
So, Professor, when you're dealing with overdetermined systems, you use least square method, and then when you're dealing with underdetermined system, you use least norm.
Yes.
All right, got it. Thank you.
Yeah, and I'm glad that somebody asked me about this specific question, that what would we do if we do not have a square matrix, maybe 2 lectures back or 3 lectures back. And these all, I mean, this today's lecture and some part of the last lecture was basically tuned towards this specific scenario where you do not have a square matrix. So, and there in real life situations, there will be many situations and many cases where you do not have a square matrix. What will you do in that situation, and what generally people do? So these specific lectures were tuned to that topic. And that topic, if you see, you will also feel or you will also find it when we will doing the chapter on interpolation or cubic or whatever degree of polynomial interpolation. We will do that chapter. You will see that this solutions are presented there, but not in the form I just written it here, like this specific matrix form. This is the most generic form. It is used everywhere. So this is what you can use for any polynomial, whether it is third degree, fourth degree, fifth degree, or any other function. You can always use this specific formulation. So that would be very useful if you happen to use this solutions, or you have to happen to solve the overdetermined system or underdetermined system sometime. Any questions, guys? Or if you have not following it, any questions so far?
I have a question.
Mm-hmm.
So what would be the least norm if we were to do like a polynomial, since we got a vector for our first equation?
So again, if you have a polynomial, it will be just like the same, but instead here you are not fitting a third degree polynomial, but you are fitting fourth degree polynomial. So if you want a fourth degree polynomial out of 4 data points, you know that you have more number of unknowns because you have 1, 2, 3, 4, and 5 unknowns, but I have got only 4 equations. Yeah. 1, 2, 3, and 4. I've got 4 equations, but there will be another term with 4th degree equation, a4x14 plus a4x24 plus everywhere there will be another coefficient. So in that case, again, it will be the same scenario, but you, instead of using this form, you are going to use the form that we used for the least norm, this form.
Okay, thank you.
Yeah, so least norm is always for the system of equations when you have more unknowns and less equations. That is underdetermined system. You have less equations, but you have more unknowns. So that is always the least norm solution. And least square is when you have more equations, but less unknowns. Then we have least square solution. That you have to remember. Okay. Any other questions, guys? If not, then we can wrap up our discussion for today's lecture, and we will come back to the, again, chapter number 11 discussion, which is numerical solutions, and we will continue our discussion with that.